Whenever we talk about how acidic or basic a liquid is, we usually toss around familiar numbers between 0 and 14. But physically, what we're actually measuring is the concentration of freely floating hydrogen ions in that liquid. Let's look at three common examples: lemon juice, pure water, and bleach. If we write out their actual hydrogen ion concentrations in standard decimal form, say in moles per liter, the numbers start to look a bit unwieldy. Lemon juice sits at roughly 0.01. Pure water is 0.0000001. And bleach, it has a hydrogen ion concentration of about 12 zeros and then a 1. If you try to compare these values by plotting them on a standard linear number line, you immediately run into a problem. If we set the far right side of our line to represent the lemon juice, pure water is so remarkably small that it effectively sits exactly on 0, and bleach is 1,000,000 times closer to 0 than that. No matter how much you zoom in, standard linear geometry just isn't equipped to show us the difference between these values. They just crowd into the origin. To make sense of a universe that operates across such vastly different scales, we need a mathematical tool that counts the zeros rather than getting lost in them. To deal with these microscopic numbers, chemists use a mathematical compression tool represented by the lowercase letter p. Whenever you see a p in chemistry, like in pH, you can translate it directly as take the negative base 10 logarithm of whatever follows. Let's see this in action. Take a hydrogen ion concentration of 0.0001. First, let's rewrite this messy decimal as a power of 10. It becomes 10 to the power of -4. Now we apply the logarithm. The base 10 logarithm asks a simple question. 10 to what power gives me this number? It effectively reaches in and grabs the exponent. So log base 10 of 10 to the -4 is just -4. But having a scale made entirely of negative numbers is a bit annoying for everyday use. That's where the negative sign in our p operator comes in. It flips that -4 into a nice, clean, positive 4. Notice what this does to the relationships. If we increase the concentration of hydrogen ions from 10 to the -4 up to 10 to the -2, which is a 100-fold increase, the pH goes from 4 down to 2. This is the source of that counterintuitive rule. A higher concentration means a lower pH. Visually, you can imagine a number line where these tiny decimal values are infinitely scrunched up near 0. The p operator acts like a magnifying glass that stretches this scrunched up space out, unfolding it into a comfortable, evenly spaced linear scale. Each step of 1 on this new pH scale perfectly represents a 10-fold change in the actual physical concentration. But hydrogen ions don't exist in a vacuum. There is another player in this microscopic dance. When water molecules occasionally break apart, they don't just form a hydrogen ion, they leave behind a complementary particle, the hydroxide ion, or OH-. In pure water, these two perfectly balance each other out. But no matter what you dissolve in water, nature enforces a strict rule. The concentration of hydrogen ions multiplied by the concentration of hydroxide ions always equals a constant. At room temperature, that constant is 10 to the power of -14. This is where the magic of logarithms truly shines. Let's take that messy multiplication problem and apply our new p operator, taking the negative log of both sides. Here we get to use one of the most elegant rules in math. The logarithm of a product is equal to the sum of the logs. So our left side beautifully splits into an addition problem, and on the right, the negative log base 10 completely neutralizes the 10 to the power of -14, simply plucking out the 14. Now look closely at the left side. Negative log of H plus is exactly what we defined as pH, and naturally, the negative log of OH- is called PoH. Suddenly, a complex equilibrium of microscopic particles turns into a remarkably simple addition problem. pH plus PoH equals 14. You can visualize this as a sliding bar of fixed length. It's a mathematical seesaw. If you add acid to a solution, driving the pH down, the math violently forces the PoH to go up to compensate. They are inextricably linked, bound together by the properties of water and perfectly illuminated by the rules of logarithms. Let's put this mathematical seesaw to work with a concrete example. Suppose you have a 0.001 molar solution of sodium hydroxide, a strong base. Because it's a strong base, it dissociates completely. meaning our concentration of hydroxide ions, OH-, is 0.001, or 10 to the negative 3. Now, if someone asks you for the pH of this solution, you might feel a little stuck. We know the hydroxide concentration, but pH is a measurement of hydrogen. To see our options for getting there, let's draw a map. Up top, we have the raw concentrations, H+ and OH-. Down below, we have their logarithmic counterparts, pH and PoH. We know the vertical paths between these realms are governed by the negative logarithm, and from our seesaw in the last section, we know the horizontal rules. Up top, the concentrations must always multiply to 10 to the negative 14. Down below, the p-values must always add to exactly 14. To get from our starting point, the hydroxide concentration, to our destination, the pH, we have two possible routes. Route 1 stays in the land of raw concentrations. To find the hydrogen concentration, we'd have to divide 10 to the negative 14 by 0.001. Dealing with 13 zeros divided by 2 zeros is exactly the kind of arithmetic headache we set out to avoid. So let's take Route 2, dropping down into the logarithmic landscape. First, we take the negative log of 10 to the negative 3. The log essentially just extracts that exponent, effortlessly giving us a PoH of 3. Now we just slide across the bottom of our map. Since pH and PoH must always add up to 14, finding the pH is as simple as subtracting our PoH, 3, from 14. And just like that, we arrive at a pH of 11. By converting our values into logarithms first, we effectively teleport past the messy world of tiny fractions, turning a cumbersome division problem into trivial grade school subtraction. Because of the way chemistry is usually taught, there is a very common misconception that the pH scale begins at exactly 0 and firmly ends at 14. But let's look at the math. What happens if we have a highly concentrated strong acid, say a 10 molar solution of hydrochloric acid? The concentration of hydrogen ions is simply 10, or to be mathematically explicit, 10 to the power of 1. If we plug that into our operator function, taking the negative base 10 logarithm of 10 to the first power, the logarithm does exactly what it was built to do. It extracts the exponent. The base 10s cancel, the 1 drops down, the negative sign flips it, and we get a pH of -1. Negative pH is perfectly valid. The math doesn't break. Our conventional 0 to 14 boundaries are just a convenient window for the mild chemistry of everyday life. And this reveals the true underlying power of the P operator. Logarithms are essentially mathematical compression algorithms. They take the extreme exponential reality of the physical world, massive leaps in concentration from the strongest acids to the purest water, and gracefully compress them into a simple, human-readable, linear scale. So next time you see a pH value, remember, you aren't just looking at an arbitrary scale. You are looking directly at the exponent.